Hey everybody, let's look at this one. This is 8E, tension and strings attached to bottom here. So it says solid cubes 1, 2, and 3 have volumes of V, V, and 2V respectively, are made of the same material. So same material means we'll have the same density for all of them. They're attached by strings shown in figure 1 to the bottom of a tank of water of density rho water, and they have tensions T1, T2, and T3 respectively. And so it says cubes 2 and 3 are fully submerged in the water, as we can see here, and cube 1 is partially submerged. So we got that teeny bit right there that's sticking above the top. So the density of each cube is rho C. All right, so I wrote rho before, it's rho C. All right, now let's look at the questions that they have. I'm going to keep that picture there because I'm going to come back to it in just a second. It says the masses of the three cubes, 1, 2, and 3, are M1, M2, and M3 respectively. Rank the masses of those cubes from greatest to least, noting ties if applicable. Man, I cannot speak today. So let's look at this. We know that the density of something is the mass per volume. So we can say that the mass is equal to the density times the volume. Or more simply, that mass is directly proportional to volume there. And since we can say that, we know then that the mass of cube 3 is greater than mass of cube 2, which is equal to the mass of cube 1. And even more specifically, although we don't have to say this, the mass of cube 3 is twice the mass of these guys right here because they have twice the volume. It says rank the tensions in the strings from greatest to least. Justify your response beyond just referencing equations. That's kind of a shame because it's kind of easy referencing the equations. I will draw a free body diagram here. So we've got the weight of these cubes down. We've got some buoyant force up. I know that buoyant force has to be greater than the weight because we also need a tension back down to balance them out here. So we can say this, that the tension is the difference between the buoyant force and the force of gravity, right? It's got to make up the difference there. So if we double V, like as in the case of 2, so if we double V, we're going to, we double the weight, right? Because of what we said before, double the mass, double the weight, but also because we double the volume by doubling the mass, we double the buoyant force. So we double the weight and we double the buoyant force there. And so we're going to double the difference between them. And so that means that tension 2 has got to be greater than the other guys there. Specifically, it's got to be greater than tension 3 is the one with 2 times the volume, and it's got to be greater than tension 2 because of what we just talked about up here. So more volume means more buoyant force and more weight, and so the tension's got to be greater. Well, what about 2 and 1? Well, if we look here, we can see that 2 is fully submerged and 1 is only partially submerged. So since T1 is only partially submerged, then it's going to have less volume of fluid displaced. And because there's less volume of fluid displaced, we're going to have less of a buoyant force and therefore less of a tension as well. So T2 has got to be greater than T1 there. All right, now, speaking of that, let's come here to, we are going to draw some free body diagrams. And so on these, let's just say that the force of gravity on cube 1 is 1 square down. Then the force of gravity on cube 2 is also going to be 1 square down. Let's just say that the buoyant force on cube 2 is 2 squares up. And so I know that the buoyant force, as we just said, has to be less on cube 1 because it's partially out of the water. So let's say it's only 1.5 up. Also, as we just discussed, the tension has got to be the difference between these. So if buoyant force is 2 up on this one and gravity is 1 down, then we need a force of tension that's another cube 1 down. So that 1 down plus 1 down balances 2 out. And over here, force of gravity 1 down, buoyant force is 1.5 up, so we would need half a brick down for the force of tension on this one. And again, reiterating what we said on the previous page, that the force of tension has got to be greater for cube 2 than cube 1. Over here with cube 3, remember what we said, if we had twice the volume, we're going to have twice the force of gravity. So instead of 1 down, we'll draw it 2 down. Also, if we have twice the volume, we'll have twice the buoyant force. So instead of 2 blocks, we'll have 4 blocks up there. And then finally, the tension again has to be the difference. So 4 blocks up, 2 blocks down. We need another 2 blocks down for the tension. And as we said on the previous page, the tension in cube 3 has got to be greater than the tension in cube 2 for those reasons. All right. Now, on to part D. So part D says cube 1 has a side of length S. Derive an equation for the tension Ft in the string connected to box 1 in terms of the depth x the box is submerged underwater, the density of water rho w, and the density of the cube rho c, and physical constants as appropriate. So it might sort of help to imagine that we've got this sort of, side to the box like this on the bottom there. All right, so let's talk about it now. Finally, since they didn't say don't reference equations, we can put an equation down here. We know that we've got the buoyant force up, and that's subtracting the force of gravity down and the force of tension down, that's got to balance out to be 0 because this box isn't moving there. They want us to solve for the force of tension, so I'll just move it over to this side of the equation, and then I'll also write the force of tension on the left side just because that's traditional. All right, so that means that the force of tension is equal to the buoyant force minus the force of gravity here. Let's start to substitute in for each of these. So the buoyant force, using Archimedes' principle, is going to be the density of the water times the volume of the fluid displaced, or we could put volume of water, times gravity. And then the weight is going to be the mass of the object, so the mass of the cube, times gravity there. All right, next up, let's continue to do some substitutions here. So we're going to replace the volume of the water displaced with the area times the height, since it's a cube. The area is going to be the base of this cube, which is s squared. And the height is up from here to here. That's the height of our cube. And so that's going to be x. And then we multiply by g. Then over here, I'm going to replace the mass of the cube with our favorite thing to replace mass with in this chapter, which is density times volume. Now be careful. It's the density of the cube times the volume of the cube. But what's the volume of the cube? It is s cubed is the side of it there. And so that is the volume. And now that's basically it. You can just leave it like that, or if you want, we could factor some things out here and clean it up a little bit. I've got s squared in each side. I've got a g in each side, so I can pull that out, g times s squared, and that leaves me with, I still have a density of water here. I still have an x there, and then on this side here, I pulled out the density of the cube, and I still have one more s here since I pulled out an s squared. And so that's sort of the simplified version of what I've got left over now in the end. So lastly, it says, justify how your derived equation in part D is or is not consistent with your ranking of the tensions on cube 1 and cube 2. Well, let's look at this. As we go deeper and deeper in there, then this term right here, x will get bigger and bigger and bigger, so this term will get bigger and bigger and bigger. So this whole parentheses here will get bigger and bigger and bigger, which will increase the tension for 2, just like we said.